Prerequisite review. There's 4 large topic areas I want to make sure that we review before we go forward in the class. So the first 3 of them are from our pure math classes, as this is an applied math course. We're going to be drawing several of these ideas together from different classes and applying them all to our engineering problems, and then going over electronic components, which you have seen before in your electrical class and your E&M class in physics. So we're going to be looking at Laplace transforms, which you saw at the end of your ordinary differential equations class. We're going to be revisiting partial fraction expansion, which you should have seen in your Calculus 2 class. And we're going to be looking at putting equations into matrix form, which you will have seen in your linear algebra class. And then again, looking at basic electric components and how they interact with voltage and current, which you saw in your electronics courses in physics and then applied in electrical engineering. So we'll begin with using the Laplace transform. Now you probably saw this at the very end of your ODE class and didn't use it very much and probably did not see much of utility of doing a Laplace transform on an ordinary differential equation. Well, we're going to actually be using Laplace transforms a lot in this course and sticking in the frequency domain that we convert into when we do a Laplace transform. A lot more of that will come in future sections. But one way we can use Laplace transforms is it's a good way to solve ordinary differential equations. That's a different technique than you probably use in the first half or 3/4 of your ODE class. So the purpose of solving an ODE is we start with some dependent variable and its derivatives in what we call this ordinary differential equation, and our task is to solve it. That is to say, solve for the dependent variable as a function of time, with the idea that once it's solved, we will know the value of our dependent variable at all points in time once time begins. So starting at time is 0 to time is positive infinity, we're going to know its value at all of those points. So the ODE is typically comprised of that dependent variable and its derivatives, and we might have external inputs as well. So maybe an input that is dependent on time, or maybe is just a constant. So the good thing about a Laplace transform that makes it a good method for solving ODEs is that we are going to be solving a homogeneous part and the particular part simultaneously. And also it's going to integrate the initial conditions into our solution right away. If you think back to when you were taking your ODE class, before looking at the Laplace transform, typically what you would do is you would solve for your homogeneous solution for your ordinary differential equation. You would put it to the side. If your ODE was non-homogeneous, that is to say there was forcing on the right-hand side of the equation, then you needed to find the particular solution. So you would find that would be based on what the right-hand side looked like. Now you would add the homogeneous solution to the particular solution to get your total solution, and then you would need to apply your initial conditions, as many initial conditions as the order of your ordinary differential equation. So a lot of steps go into that to get your closed form total solution. The Laplace transform, as we're going to see through the examples, does all of these steps kind of at the same time. And it can, depending on what the equation is we're dealing with, the ODE that we're dealing with, it can solve them quicker and easier than some other more general methods that you might have looked at. It's going to depend on the order of the equation. It's going to depend on what the forcing is if it's a non-homogeneous equation, but oftentimes it can be quicker and easier. So kind of the basics of what we're doing is we're going from our time domain, that's our original independent variable is time in our ODE, and we are going to the domain of frequency, this S. So we're going from this T to this S. So formally, what we're actually doing is we're taking our original function, and when we do a Laplace transform, we're taking that function, we're multiplying it by this exponential, this e to the negative st, and then doing this integral from 0 to infinity, and that is by definition what a Laplace transform is. Now, in practical terms, we're not actually going to be doing this infinite integral. We're not going to by hand be integrating our f of t to get our f of s. We are going to be using Laplace transform tables that have already done that for us for common f of t's, for common functions, how we go from the time domain to this frequency domain, and also how we go back. Because what we're going to be interested in, and I'll illustrate it on the next slide, is we're going into this frequency domain, and then we're going to want our solution oftentimes back in the time domain. So graphically, what does a Laplace transform do? How are we at least going to be using it in this section? So we start down here. We are, at least just in the pure mathematical terms, presented with an ODE that's in the time domain. Now, a lot of our job in Unit 1 in the modeling part is creating that ODE and then going through these steps later. But let's just say for now we're given an ODE. Now, where do we want to get? We want to solve it. That is to say, let's say that x is our dependent variable. Our ODE will have an x dot, an x double dot probably in it. Now, one way we can go from our given ODE to our solution, which is in this bottom right box, we want x of t equals whatever the solution is. Well, we could just go directly there, and we can solve our ODE for our dependent variable using calculus. And again, this is probably what you did in the first half or so of your ODE class, is you might have found the characteristic equation, or you had some rules that said if your ODE is in this form, this is what the solution looks like. So we used calculus to go from the presented ODE to our solution. And that can work great. Depending on the equation, that might be easier or harder to do. And like I alluded to on the previous slide, this step from going from bottom left to bottom right, you need to solve your homogeneous, your particular solution, and apply your initial conditions. Some of those steps might be easy or not to get down here. All right, now, what does the Laplace transform let us do? We still want to go from the bottom left to the bottom right, our solution, and what the Laplace transform lets us do is kind of sneak around what can be this difficult step of solving for our variable using calculus. In some ways, what we're doing is we're turning it from a calculus problem into an algebra problem. So what we're going to do is take that original ODE in the time domain, and we are going to be taking the Laplace transform of both sides of that equation. And now we have our same equation, but now everything is in the frequency domain. Everything's in terms of S, or more specifically, the Laplace frequency domain. So we've converted everything from t to s. We are doing those Laplace transforms. So now we're taking that transformed equation, and like I said, it's kind of turns it into an algebra problem. We want to isolate our variable, our dependent variable, using algebraic techniques. And when we do that, we're going to get an equation that looks like, again, I'm using x here as my dependent variable. We're going to isolate this x, big X of s, the Laplace transform of x, equals some stuff on the right-hand side. It's going to be constant terms, it's going to be s terms. Once we've isolated that x of s, then our goal is, well, we don't want our solution in the frequency domain, we ultimately want it in the time domain. So then what we can do is go back from the frequency domain to the time domain using an inverse Laplace transform. That's what's going to take us back. Now, there is some difficulty on the right-hand side here because we might need to do some algebraic manipulation in order to get something that we can more easily take the inverse Laplace transform of. But again, everything up here is really algebraic steps rather than calculus steps. So then in the end, we can get our solution back for x of t. So it's an alternate method to get our solution in the time domain. So how do we actually do these steps? Let's look at our solution procedure now in words instead of graphic. So again, we're going to take our given ODE and we're going to transform everything from the time domain to the frequency domain. We're doing a Laplace transform. when we look at the Laplace transform table, at least the example of one, we're going from the left-hand side to the right-hand side in this step one, getting everything into terms of S rather than terms of T. Then what we want to do is isolate our dependent variable. Here I'm using f as my generic dependent variable. We want to get that by itself. At this point, this is an algebraic step of what we're trying to do. Just isolate that f of s on the left-hand side, and then the right-hand side is going to again have these s terms and constants. Now there might be some, I'll call it algebraic tricks here that we need to implement, such as partial fraction expansion, which I'll talk about next, polynomial division, completing the square. We need the right-hand side to look like something that we have on a Laplace transform table, because that last step is we're doing an inverse Laplace transform. We're going back from the S domain, frequency domain, into our time domain, t. So depending on how extensive a Laplace transform table you have, maybe you have a more extensive one than the one I'm going to show in a moment here, but it needs to be on that table so that we can relatively easily do this step. And once we do our inverse Laplace transform, we're back in the time domain, and now we have our solution. And again, this solution encompasses the homogeneous solution, the particular solution. They've been put together, and our initial conditions have been implemented as well. So how do we go from the time domain to the frequency domain? How do we go back? Well, we can use a Laplace transform table. Again, by definition, the Laplace transform of some function is going to be that infinite integral that was presented earlier. We're not going to be doing that integration. This is a table of the more common types of functions that we're going to see, and how we go from t to s and how we go back from s to t. So it's a relatively short list. There's definitely more extensive ones out there, but for this course, this table is going to be thorough enough for the types of equations, the types of functions that we're going to be seeing. So if we see here, I have it in two columns here, but let's just say on the left column here, this is going to be our function in the time domain. And if we want to take the Laplace transform, we're going to go from the left side to the right side. So for example, this second rule here, this e to the at, this exponential raised to the at power, when we go from the time domain and take its Laplace transform, it's going to go to 1 over s minus a. So again, depending on what that a is going to dictate what this fraction is going to be. And then if we have just some dependent variable, like here I'm using f, but we might use x, or it could be I or v if we're in electronics. Whatever our dependent variable is, here are the rules for going from its time domain. We take its Laplace transform and then what it becomes in the Laplace frequency domain. So generically here, a lowercase variable, if it's a dependent variable, is going to indicate that it is time dependent, and then the uppercase version of it means that it is frequency dependent, or it's the Laplace transform of the lowercase value. So I have this in the course materials in a PDF form, or you can refer to it here when we want to do Laplace transforms. And when we want to do an inverse Laplace transform, like when we get an expression in the form of 1 over s minus a, something that looks like that, to take the inverse Laplace transform, we're going to go from right to left. So when we go back into the time domain, that 1 over s minus a is now going to be in the form of e raised to the at power. So we're going to see through some examples applying our Laplace transform and the inverse Laplace transform next. But before we get there, there are Laplace transform rules that are going to be really useful when we are solving ODEs via the Laplace transform. So first, if I want to take the Laplace transform of some constant times a function, so a has to be a constant here times some function f of t, what I'm able to do is pull that a outside of the Laplace transform. So we see here, this is the same as a times the Laplace transform of little f of t. Now I can do the Laplace transform of my dependent variable, and then the Laplace transform of little f of t just becomes f of s. Big F of s is the Laplace transform of little f of t. So this is also showing that the only things affected by Laplace transforms are functions of time. F of t is a function of time. I cannot pull it out. A, if it's a constant, is not a function of time. It is not affected by that Laplace transform. Right, the next rule we're going to use is that the Laplace transform of the sum of functions is the same as the sum of the Laplace transforms of those functions. So I have the Laplace transform of some function f plus some function g. I can split that sum out, and it's the same as the Laplace of f plus the Laplace of g, which then, here if f and g are just dependent variables, just become big F and big G. This is also true for differences. So if it's a plus or a minus, or if it's f and g and h, I can keep going here. So if it's 2 terms or 3 terms or more, this rule is still going to apply. Right, these two rules also apply for inverse Laplace transforms when we're going from the frequency domain back into the time domain. So we see here this third line, that's the same thing we have up above, but it's the inverse Laplace. I can take a constant outside and still operate like I did in rule number 1. And then in this fourth rule, it's also true that the inverse Laplace of a sum is the same as the sum of the inverse Laplace transforms. And again, if I have 2 or 3 or 4 or however many terms, that's still going to apply. And if I'm adding or subtracting, that rule is still going to be good. All right, so here in red, I want to make sure it's clear this is not a Laplace transform rule, even though we would like it to be. So again, in rules 2 and 4, if I'm taking the Laplace or inverse Laplace of a sum, I can split it out into the sums of the Laplaces or the inverse Laplace transforms. That is not true, however, for the product of two functions, f and g. So the Laplace transform of function f times function g is not the same as the Laplace of f times the Laplace of g. This is also the case for quotients. If I have the Laplace of f over g, I also cannot say it's the Laplace of f over the Laplace of g. So sums and differences, yes, that rule does apply like we see in 2 and 4, but for products and quotients, we cannot do that. We have to, maybe if we're in a case where we have the product of two functions, we might have to do some algebraic manipulation of that function to get it to look like something that we have on the Laplace transform table. And if you look at the more extensive Laplace transform table, the Laplace of a function is going to turn out to be a convolution integral, which we're not going to get into in this class. But keep in mind that this in red is not one of our Laplace transform rules, but looking at these other 4, these we are going to apply while we are solving problems, specifically ODEs, and trying to get a solution via the Laplace transform method.